Good morning, everyone. Welcome to Engineering Tomorrow's Astrodynamics Special Lab event. We are so excited and happy to have you guys here with us today. Hope you're ready to have some fun designing and testing those balloon rockets. We hope to see and hear from lots of you guys. We have an amazing, out of this world, astronomical level keynote speaker for you later on, but also a pretty amazing engineer presenter that I will hand it over to now. So I'm happy to introduce to you Miss Lauren Sawyer.
All right, Jillian, with the puns this morning. Those are pretty good. Good morning, everybody. I am so excited to introduce this lab to you guys today. I love this astrodynamics lab. It is so near and dear to my heart, which we will get to in a little bit. Let me go ahead and share my screen and we can get this lab started. All right, now can everyone see that?
Yes, we can.
Perfect. All right. Well, good morning, everybody. Welcome to the live Engineering Tomorrow Astrodynamics Day. I love this lab. It is such a fun one, and I hope you guys think so too. Your goal today is to learn how to send a payload from Earth into space, or something equivalent to that with the time we have today. So, to introduce myself, my name is Lauren Sawyer. I am a research engineer at Leidos Innovation Center. Basically, that means that I work on the edge of the technology world today. So, I develop new things, specifically for autonomous vehicles and navigation. Now, you might be seeing the ocean in my background and the ocean in this picture right here. So I actually am an ocean-centered engineer. So I work with vehicles that go underwater most of the time and trying to figure out where they are in space and time. But that being said, I actually got my undergrad degree in aerospace engineering. And that didn't fall to the wayside. I actually still work on a couple satellite projects. And so I use my experience in navigation to figure out where the satellite is in its orbit. And satellites are really good at taking pictures of the ocean surface so that we can collect a ton of data. So space and ocean, they work together super closely. They're very similar in all of the different kinds of science that I deal with on the day to day. And it's a really exciting kind of overlap. And you'll actually get to hear more about that with our keynote speaker, the overlap between air, space, and water. And then I also got my master's degree in ocean engineering just to kind of solidify that ocean track. And I got that at University of California, San Diego. Now, this is the breakout development team. This is the team that developed the lab. And if you see a sort of familiar younger face on that, I was one of the, at the time, engineer college mentors that helped develop this lab a few years ago when we debuted it. And I want to shout out Milton Davis. He was just such a wonderful mentor and engineer, and he really led the engine for creating this lab. And working with Katie and Travis was also such a wonderful experience. This lab got redeveloped about a year or two ago, and Betsy was able to lead that effort, and she is online today. So she's going to be sharing all of her expertise with you guys, and she's so brilliant. She's got the fun space background. So, and then shout out to Brianna and Molly for helping us redesign this lab. So this is the lab overview. You will be learning about spaceflight history, launch vehicles, payloads, and what a payload is, and then missions in space. So it sounds like a bunch of different stuff that we're going to be getting to, but I will break it down for you all so that you can learn all about it in this next half hour. And then what you will be doing is you guys are going to be building and testing a rocket. And it's a balloon rocket, which is super fun, but it has all of the same kinds of mechanisms that we do in rocket science. So we will be making a lot of analogies for you guys. And then you're also going to be looking at performing maneuvers in space. Let's outline the type of engineering that this lab uses. So it's called aerospace engineering, and both aircraft and spacecraft are used within and outside the Earth's atmosphere. And as I alluded to earlier, even in the ocean. So we design for the specific type of environment that we will be flying in. Spacecrafts are designed for that zero gravity kind of vacuum-esque, no atmosphere environment. Aircrafts, we have the oxygen, we have the CO2, we have all of those elements that are in our atmosphere at different levels depending on how high you are above the earth, and we have to design each of these aircraft for those specific environments, whether they're going to be flying in the troposphere or the stratosphere or the exosphere, which we will get to what those all mean a little bit later in the presentation. And then underwater, we even have to design for the pressure of all of that water on top of us. So we have all of these different kinds of environments when we're designing vehicles, and we really have to think about what is this vehicle doing and why are we designing this vehicle in the first place? Like does it what is it trying to accomplish? Is it a passenger vehicle? Is it going up to space? Is it carrying something specific up to space? And that's where you get your aeronautical or your air side and your astronomical or your space side engineering. All right, so I want to see in chat a little bit of what comes to mind when you think about space. So I see that some schools are able to type in chat, and I really want the students to think about, are we alone in the universe? Is time travel possible? So everyone take a couple minutes and type in chat what comes to mind when you think about space. For me, it's just vastness. I mean, space is so never-endingly huge. And I can't fathom all of that space, pun intended. And so that's why I like the ocean, because it's finite, it ends. So that's my 2 cents about space. We've got aliens, gravity, different planets, a lot of aliens. Yeah. So, actually, one of the papers that I just read, because as a research engineer, I like to stay up to date on research that comment or upcoming research that people are doing, is in, I think, Chile. They're creating or they have a telescope that is able to see through the atmosphere of different planets and is able to determine the size and distance from its closest sun. And it turns out that there's this inhabitable zone of how far away planets are from their closest star or their sun. And if it's within this inhabitable zone, it's able to create water just like our planet created water. And it might one day, or in the past, have been inhabited by aliens. So we are actively looking for planets that can support life, which is super, super cool. And we're definitely getting better at it as our cameras are getting better and better, as our telescopes are getting better and better. All right, what is the farthest distance so far that a manned and unmanned spacecraft traveled into space? We got a question already. And I would say that for manned, I'm pretty sure it's just the moon. So that's, I mean, just the moon. It's already such a huge feat to go to the moon. But for unmanned, we have gotten to Mars. You guys have heard about the Mars rovers, I'm sure. And then I think we've sent unmanned spacecraft into orbits of planets further out. So we are definitely working on that manned versus unmanned. And I know that in the next, decade, people would love to send people to Mars to be able to explore it. That is kind of one of the big ultimate goals of the space research industry. So now we're going to talk about past, present, and future of spaceflight. So I've got a little overview for you guys. Spaceflight is brand new in the scope of history. So less than 100 years ago was when we first started thinking about space. So in 1957, the first satellite was sent into space by the Soviet Union. It was the Sputnik 1. And then in 1958 through 1963, the United States was able to catch up during that space race and sent its first man in space program. So the first American in space was in 1961. And then in 69, the first people were on the moon, and they were sent by a NASA Saturn V space rocket. So that's the famous moon landing that we've all heard about. 1981, we were able to build the space shuttle, which was really, really large in the space industry because it was the first reusable spacecraft. So it went up and it came back down, and then we were able to send it up again. And the amount of forces that are on these spacecraft when they get sent up into the atmosphere so intense that the fact that we could actually use something again and again to send people back up and down into space was such a technological development, because that means that the materials that we used to build the space shuttle did not burn up in the atmosphere, and all of the fuel cells were able to be reloaded and refilled. We could, basically use this like a car to go to and from space. It's such a crazy, crazy development, and it's amazing that we did that in 1981, so 40 years ago. So in 2021, the SpaceX Falcon 9 was built, and it's the record holder for the most satellites launched by a single rocket. It launched 143 satellites. And so this was the development of smaller satellites in what's called low Earth orbit, or LEO. So there are two different kinds of orbits above the Earth. There's low Earth orbit, and then and I'm forgetting what the G stands for, but there's GEO, which is just a little bit higher than the low Earth orbit. And most of our satellites for GPS were in that GEO sphere around the Earth. And what SpaceX really pioneered was sending many, many, many satellites into that low Earth orbit for different kinds of, oh, thank you, Betsy, geostationary satellite orbits. Because she's also an aerospace engineer, a phenomenal aerospace engineer. But so we sent a bunch of satellites into that low Earth orbit, and that's what we're using a lot for the imaging of the Earth's surface. So we can, like I said, take pictures of the ocean surface, gather a lot of scientific data about that, and it offers a lot more coverage of the Earth as a whole because we have more satellites up there. So as they're orbiting, we can see a lot more of the Earth's surface at any given time. This is a huge development in science. And then in the 2030s, we would love to be able to put people on Mars. And so multiple companies are planning missions to the moon and to Mars in the future. And that is really the technological edge of where space development is going. All right, another engagement question. What would you guys like to investigate in space? Now, I already saw a bunch of aliens, so think of another thing that you think would be really cool to investigate in space. And mine would probably be what kinds of planets, like what are the chemical compositions of the planet atmospheres, and how does the size of the planet determine what the chemical composition is, if there's any kind of relation. So we've got some black holes, and black holes are super interesting. People are making really, really intricate mathematical models of black holes. And as far as our knowledge goes, these mathematical models, so they're just using calculus to model what's going to happen around the black hole. And they're pretty accurate as far as we can tell. It's very, very amazing to see that the math is so, so related and so accurate to what we're seeing in the universe. So we've got other life in our solar system, finding other planets with other species, dwarf planets, stars, and supernovas. Okay, Challenge Preparatory Academy, you guys are really covering the gambit there. Area 51, and have we ever explored the dark side of the moon? Memorial High School, that's a great question. So basically, yes, because the moon is just another rock sphere. Just like the Earth is a kind of spheric, planet, the moon is, another spheric planet. And so whenever we see the light side of the moon, that's basically what we see from the sun's radiation reflecting off of the moon back to us. So that changes depending on how the moon is rotating around the Earth and what we're seeing of the moon. So as long as we're able to explore, the entire sphere of the planet, and it's got much, much less of an atmosphere. So that's why people bounce super, super high on the moon. Yes, we can explore the dark side of the moon because that is really just what part of the moon that the Earth can't see. It's out of the viewpoint of the Earth and where the sun is reflecting off of it. So that's a really good question. Asteroids is a really great answer, and never-ending expansion of the universe. Yeah, that part freaks me out. I can't believe that the universe never ever ends. It's crazy to think about. So we got some phenomenal answers. These are some things that we are currently investigating in the space realm. And so we are doing orbital servicing and manufacturing. So basically, we've got a lot of clutter in the low Earth orbit and the GEO. And what we want to do is we want to make sure that instead of sending more and more satellites up there, we want to fix what's already up there. We don't want to create more clutter, more space junk. We want to be able to be reusable and think about the future of, the materials that we're using, et cetera. So servicing and manufacturing is a really, really big aspect of science in the field of astrodynamics. And then we've got space weather monitoring. So different kinds of planets, and especially the sun, the solar flares that the sun exerts on the surrounding galaxy around it. We want to study those patterns. We don't really understand a lot of why those events are happening, or can we predict them, like how we've gotten our atmospheric weather down to a moderately predictable science. We want to be able to do the same for space weather events. We've also got astrophysics. This is in relation to black holes and stars, and along their decay of being, our star is along the decay of being like a red giant to a white dwarf, et cetera. And so stars can start out super, super brighter than that, or they can be farther along that decay process. And so we want to understand really what are these events that are surrounding stars and black holes, et cetera, like a lot of you guys were pointing out. And then space communications. So space communications is a super, super important part of space research. And this is actually something that I play a big part in because we want to be able to send the data that our satellites are collecting back to some ground station. So how do we do that? I mean, it's all the way up in space and we're all the way on the ground. And so we have to be able to, like GPS sends bits and packets of messages, we have to be able to send those same packets of messages to the ground station so that the scientists and engineers down here can take all that data and they can learn so much more about either the Earth or space around us. So data communications and space communications is a really, really big aspect of the science and the research that's going on in space right now. And then my personal favorite is Earth and planetary environmental science. Let me get a mute on. Thank you so much. So Earth and planetary environmental science is how we can use our satellites and our things that are up in space to observe more about the Earth and the planet that we live on. And one of the coolest things that I think I learned about space is that we can see chlorophyll concentrations on the surface of the oceans. And so chlorophyll is what basically the phytoplankton are. It's the green pigment in leaves and the phytoplankton that are in the ocean, those primary producers that absorb sunlight and turn it into energy. They're exuding chlorophyll as well as like leaves would. They're closely related to plants. And so we can actually see them from space because they only stay in that upper layer of the ocean. And so we can tell how much production is going on in certain areas of the ocean. So because the primary producers, the phytoplankton, are the start of the food chain, after that is going to come the small fish, then the big fish, then the bigger fish, some marine mammals. So we can see the beginnings of the food chain all the way from space, and we can monitor that and we can keep track of which areas of the oceans at what points in the year, so summer, spring, fall, winter, are being these production centers and where the fish are going to go, where we should send fishermen. And we do that all from space. This environmental monitoring is so integral to sending satellites up and getting more data. So the advent of space in science is all about more data collection for us planetary scientists and engineers. And it's so, so cool. All right, now this is where you guys come in. What do we send up to space to help us achieve the mission? And we call that a payload. So the payload is the object that's being carried by the launch vehicle or the rocket. And we also do need food for our astronauts because they got to eat something. So examples of payloads are actually the astronauts themselves can be considered payloads. The satellites that I was just talking about, rovers like the Mars rover, it didn't just fly up to Mars by itself. It needed to be sent on a rocket. And then some design constraints include how big do we make this launch vehicle? Well, if we make it bigger, we have to give it more fuel. So can we make it as small as possible so that we can send it up with the minimum amount of fuel and the minimum cost? You know, as engineers, we really have to play this balance game, this optimization game of I want to be able to fit my payload. I want to be able to put enough fuel in it. I don't want it to, get stuck or have just too little fuel to get to the moon, for example. And so we have to figure out what the best design is given all of our design constraints. So what is a spacecraft? Because that's the thing that you guys are focused on building. A spacecraft is a vehicle or machine designed to travel in outer space. So this can be some payloads of the launch can be spacecrafts themselves. So for example, if we're sending a rover, up to space, it can't get through our Earth's atmosphere by itself. But maybe once it's in space, it has enough of a launch system to be able to navigate. So it launches from the spacecraft itself and then it's able to fly itself and land on, say the moon if we're sending a moon rover. And spacecrafts are also the rockets that we send to get out of the atmosphere itself. So we have a bunch of different examples of payloads here. We have the Apollo lunar module, the Hubble Space Telescope, which takes phenomenal pictures of extending space in the universe. And we've actually just sent up a couple years ago the James Webb Telescope, which has provided us wonderful pictures of the universe and beyond, some black holes that are of more detail than we were ever able to get with the Hubble Space Telescope. And then the International Space Station is also a spacecraft because it's able to maneuver itself while it's in space. So how do we get payloads into space? That's kind of the big ticket question. This is the Apollo 11 launch that we're going to watch a little bit of. And this is basically combining chemistry, electrical engineering, mechanical engineering.
T-minus 15 seconds.
It's how we get rockets up into space.
12, 11, 10, 9. Ignition sequence starts. 6, 5, 4, 3, 2, 1, 0. All engine running.
What's breaking off right now are actually the support that made sure that the rocket was standing upright. Now it's using its fuel to launch from the surface of the Earth all the way up through the layers of the atmosphere. So it's a really, really big chemical process that we'll delve into in the next months.
We've got a roll program.
And you can see how big, essentially an explosion this is to be able to generate this much power as it's flying. All right, so we're going to cut the video there, but that's essentially what you guys are doing today. You're going to do this with air as your chemical source, chemical power source instead of rocket fuel. And then, so what is space? This is the slide that I was alluding to a little bit ago when I was talking about the different layers of the atmosphere. And we're designing different vehicles to be able to withstand these different properties of these different layers. So we are currently in the troposphere, and that is where commercial airlines fly. We've got stratosphere, we got weather balloons that actually monitor weather pressures and systems moving up in the stratosphere. And then the mesosphere and the thermosphere are above that. And then we've got the exosphere, which is where our satellites tend to orbit around. And these are the 5 layers of the atmosphere that we typically see and we study. And this is kind of what we have to be able to navigate all the way through, because a rocket has to make it through all 5 of these layers instead of maybe just living in the stratosphere or the thermosphere. It has to go all the way up to the exosphere to deploy that satellite, or even beyond if it's getting, say, to the moon where the atmosphere stops to exist. So, how spacecrafts travel to space, you've got the different parts of the rocket, and I want you guys to definitely pay attention to this. It's a great NASA diagram of the parts of the rocket. And so, as an aerospace engineer, we study not only just the payload or maybe not only just the fuel, but how each of those parts relates to one another. So, we want the payload. And we call this an efficiency ratio. We want the payload to be, most of what we're using to send the rocket up to space, because that's a very efficient rocket. It doesn't require a ton of extra, fuel and oxidizer. It doesn't require all of that propulsion system to send the payload up to space. So 100% efficient rocket is where it's just the payload. A 1% efficient rocket is basically where the payload's 1% of all of this propulsion system that's needed to take this tiny, tiny payload all the way up to space. We want to balance that efficiency percentage. And so there are all these different kinds, or all these different parts to the rocket itself. And we've got engineers who focus just on the propulsion system, engineers who just focus on the guidance system. I am an engineer that definitely focuses on the guidance system. So I do navigation and guidance. And typically I do that in the earth, in the atmosphere, but it's the same kind of principles that can be applied to guidance up in space as well. We have different landmarks, we have different things that are telling us where we are in space and time, and we have different sensors, but the principles are very much similar. And then we've got materials engineers who are developing the nose cone. They're, studying how the material can withstand all of these different forces on it. So we need so many different people to work together just to create this one rocket that successfully launches up into space. It's very much a team effort. And then propulsion, this is actual rocket science, guys. So you can say I did rocket science today, which was my favorite thing to say in college. Whenever my friends were bugging me that I couldn't hang out, I'm like, guys, I'm doing rocket science. So, it's definitely a bragging point. But so we've got the common types of engines. We've got a solid rocket engine, which is basically solid propellants. Think of it like, if your gas wasn't a liquid in your car, it was a solid, and you used a fuse to set it all off. And so this creates a chemical reaction that we actually can't stop. So solid rocket engines are really efficient. They provide more thrust than, say, a liquid rocket engine could. But we can't stop that chemical reaction once it starts, because it starts by lighting a fuse, and then all of that propellant burns up. And so unless we have like spacers in the rocket, so like different sections of the rocket that are being lit at different times, all of that solid propellant burns off. And then liquid rocket engine, this is exactly like the gas in your car tank. So you can step on the gas and you'll drive faster and you'll use more gas, but you can also keep your foot off of the gas and you'll stop using gas. So we can control how much of the tank that we're using in a liquid rocket engine, but it provides less thrust than, say, a solid rocket engine would. We usually use solid rocket engines to get out of the atmosphere and liquid rocket engines to maneuver once we're in space. And this is what you guys are going to be doing. So you're going to use all of these different ideas that I just talked about, and you're going to be designing a balloon rocket. And so these are your tools. You guys have got balloons, fishing line to be your struts for the launch itself. You're going to have rubber bands, straws, paper clips, balloon clips, and you guys are going to use air as your solid propellant to be able to launch your balloon up as far as possible. So remember, I said solid propellants, you can't stop them once the launch begins. And that's kind of what letting the air out of a balloon is going to be akin to. So once your balloon starts launching, there's no stopping it. There's no pulling off the gas. It's just going to go straight up. So engineers use rockets to get payloads to space, and you guys are going to mimic that process by getting a payload, which is whatever you're attaching to, the top of your balloons. It's going to be a cup of paper clips up to space or up through the atmosphere, and your balloon will be your rockets. So your goal is to construct a balloon-powered or air-powered rocket that carries the most payload, the most paper clips up to space. you all will use the engineering design process. So hopefully you guys can get a couple of iterations or a couple rounds of testing in through this live lab day. And we find that the second or third time people do this lab or do this iteration, they have their idea for the first rocket, then they test it, they find out what's wrong, they do a second, a third, maybe even a fourth one, the better it gets or the more creative it gets, because you get to learn everything that goes wrong in your first launch, and then you get to make those changes in the second and the third one. So really try to use this engineering design process. Remember that it is cyclical and there is no beginning or end. You use what went wrong from your previous launch to contribute to your design in your future launch. All right. Are you guys already coming up with some questions and ideas? I hope so. I'm so excited for you guys to try to do this lab. It's such a fun one. I had so much fun building this lab. There was a lot of balloons being shot to the ceiling. I don't think my dog liked it as much as I did. But it's such a fun one. And these are some design ideas for you guys. You can create fins to help guide your rockets. You can use dual engines or multi-stage rockets. So that's when the air from the first one goes all the way and then the air from the second one starts going. It provides you more power, maybe a little more control. And so these are just some ideas that you guys can think of. And the multi-stage rocket is what we consider staging. So one engine being used up before the second engine starts. And so that would be, in this example, the purple rocket being all the way used up, and then the blue rocket takes off. And it provides power for longer periods of time. So if you need longer exposure to all of that air power to send you up to the ceiling, think about using a multi-stage rocket. So we've got some videos if people need ideas. I think I'm supposed to be wrapping up now. So I want to get you guys to
Hey guys, so today I'm going to show you how to pump up.
Sorry, I want you guys to get started building and get started with all of your different ideas. And so we've got some example launches, and I'm just going to really quickly show this single boost launch. So you can see it uses all of its air power to go to the ceiling. Got a multi-stage launch.
Oh! One.
There we go. And yeah, I really hope you guys enjoyed this lab, and I'm actually going to hand it back off to Jillian. I want to leave you with these parting thoughts of, different ways to design your rocket and different ideas as you think about this lab. But with that, I'm going to stop my share.
Lauren, what a fantastic introduction. I know the students are just over the moon and just ready to get their hands on those kits, right? So let's give them some space. Open up those breakout rooms. They're really gravitating towards it. Okay, I'll stop. Let's open up those breakout rooms, guys, so you can get started. I know you're excited. We cannot wait to see these launches. We'll meet back here at 11:30 EST. We have ET staff in that breakout room. We have college mentors in that breakout room to assist. So let them know if you have any questions at all. But most importantly, have fun, and we'll see you soon.